get started. So we have Dr. Tarun Rambha here with us today. Dr. Rambha is an assistant professor at the Indian Institute of Science at Bengaluru, and he's an affiliate faculty member at the Center for Infrastructure, Transportation, and Sustainable Urban Planning. He did his PhD at UT Austin with Steve Boyles, right? And also did a postdoc at Cornell with Lindsay Mildred and with Richard Davidson at the University of Delaware. Okay, so his talk today is related to the work that he did with them during his postdoc in terms of hurricane evacuations. I think we have a lot of interest in that topic area being in New York City. So let's welcome him.
Thanks, Joe. Thanks for having me, and it's been nice to visit NYU. I've been wanting to do it for a long time, especially when I was at Cornell. So this was some of the work that I started towards the end of my postdoc. I was wrapping up and then got roped into some demand estimation. So I'm primarily a networks person, but then there was some dynamic programming in this thing. So I thought, okay, let me try and study this topic in greater detail. So I'm gonna present a few ideas in these categories. The first, I'll just introduce the problem and then talk about static choice models. I'm assuming everyone knows it, but maybe it'll just be a refresher. Then I'll talk about the theory behind dynamic choice models and how we've applied this to hurricane demand evacuation. So on an average, there are about 1.7 hurricanes that strike the US coast, and it seems like the frequency has been increasing over the last few years. And these often tend to trigger large-scale evacuations, which look something like that. And it's not a pretty sight because there are a lot of massive traffic jams, and all the other consequences of that makes life uncomfortable during these phases. We've had some back-to-back hurricanes in the recent past. So this is a meme that I picked up from the internet. So there was Hurricane Matthew, and it was followed by Hurricane Nicole just within like a span of a couple of weeks. So this makes it even more challenging and necessary to be able to study hurricanes and how people react to these evacuation orders and so on in greater detail. Okay, so just to give you some numbers about how severe these evacuations have been in the past. During Hurricane Rita, about 3 million individuals evacuated from the Houston area around the same time, and they were just going to neighboring cities like San Antonio and Austin, which were about 3 hours away on a regular day, but it would take about 12 to 20 hours to clear during that period. And during Sandy, maybe, I don't know if some of you might have been here, a lot of signals were dysfunctional, the traffic lights, and the emergency services would witness a lot of calls, and people couldn't talk to someone and be able to weren't assured that they would be safe and so on. Okay, so the goal is, if we can understand the demand for travel during these periods, we can use that as inputs to traffic assignment models, and then that models can tell us how congestion is going to evolve, and that can again help us understand where do we design shelter locations and things like when do we issue effective evacuation orders, when should they be voluntary, mandatory, and so on, as well as contraflow strategies. When should we make a two-way street, a one-way street, and so on and so forth. Okay, so this is the broad idea of being able to predict the demand accurately. Okay, but then the choices that individuals make is a bit complicated than that they make in regular commute traffic, where they're just picking a certain mode or time of day and so on. Okay. So I'll just give you a very quick overview of static choice models. Like I said, most of you might be familiar with this thing. Maybe this just helps to get accustomed to the notation. So when you look at standard choice models, we have a bunch of alternatives, and these are finite in number, and individuals are assumed to choose from these finite set of alternatives. And then there are these two components that are critical. One is an observable component that the analyst as well as the individual knows. Okay, so this, we'll call it as U, and it's a function of a bunch of attributes. Okay, so these attributes could be for instance, in the case of mode choice, they could be travel time, cost, and so on and so forth. And then A here represents,
Yeah, the laser pointer doesn't work.
Oh, does it work? Okay, okay. So the A here represents the alternatives. It could be bus, car, two-wheelers, or that's common in India. So these observable components, in addition to this, there is also something called a latent component, which is observable only to the decision maker and not the analyst. So for instance, you might have a preference over a bus with a Wi-Fi. Okay, so but then the analyst might not know or might not have the data that which of the transit services have Wi-Fi and which don't. Okay, so there are these other factors that individuals use to make decisions, and finally what they come up with is like they take the observable component of their utilities or disutilities, to which they add the latent components, and for every alternative A, they are computing this particular sum and then finding the maximum of that, okay, the one that gives them the maximum utility. So the individual's problem is simple. They in their mind, this is the calculation that's going on. They compute a bunch of numbers, find the maximum of that, and that's what is being picked. But on the other hand, the analyst again doesn't have access to the epsilons. The analyst only knows the first part of this expression. So let's just take a small example. So if you consider two choices that individual can take, well, let's say a car or a bus, and the attributes that the individual is concerned is with respect to travel time. So if the individual knows what time, how much travel time he or she might incur while taking a car versus a bus, so we typically parameterize the utility functions, and so the utility of taking a car given the set of attributes is a linear combination of a constant term and then the travel time incurred because of taking the car and some latent variables associated with the car. Okay, so that could be ride, comfort level, and what you might have access to your radio and so on and so forth. On the other hand, the utility that you get from taking a bus when you know your travel times of the car and the bus is simply we don't have a constant here. It creates what we call as identification issues. We just take the travel time of the bus and then some other features that the bus option might provide. Okay. Now, if we knew that the individual chose car, and let's say this came from some survey data or revealed preferences, then as an analyst, the probability that we got it right, that we predicted that the individual chose car, is when the utility that the individual gets from picking car is greater than or equal to the utility from picking a bus. Okay, and so you can rearrange these terms and you can write it as the probability of a difference of two random variables is greater than something that you know. On the right hand side, it's a function of these parameters beta, but TT car and TT bus are known to the analyst. Now, there are multiple ways in which the field progresses from here, depending on the kind of assumptions you make on these error terms. You can come up with closed form expressions or not, then you might simulate things, you might add correlations and so on. But one of the simplest options is to assume that these error terms are extreme value, time for an extreme value distributed or Gumbel. And that lets us come up with these choice probabilities in a very simple closed form, which looks like this. So this is the probability that you choose an alternative A when you are given a state vector. This is, let's say it's the probability of choosing car when you are given that the travel time of the car and the bus are known. It can be just inferred from this particular expression. And the idea with all choice models is that these probabilities are now parameterized with those betas that we saw in the last slide, and then you want to uncover them from the data that you've collected through sampled or stated or revealed preference surveys. Okay, and you do this for every different individual, so you can add an index n to indicate that it's for individual n that all this computation is being done. Okay, so like I said, you can take the choices that are made by a single individual or multiple individuals, and then come up with a log likelihood function, which looks like this. So this is the probability with which an individual n chooses an alternative an, given that he or she observed a state vector xn, assuming some coefficients beta for your utility functions. And then you're multiplying this over all the observations or all the samples that you have, and you construct this likelihood function. And then you take the logarithm on both sides and come up with the log likelihood function, and this is what you try and maximize. So this gives you the best fit for the data that you have. And the goal is to find those parameters betas, which give you this best fit with respect to the data that you collected. Okay, so this is this basic framework with almost all choice models. Is this clear? If you have any questions, please feel free to interrupt me and ask me in between. Okay, so what's different with dynamic choice models? There are many situations in which individuals just don't make a single choice and the process ends. That's not how a lot of the decisions that we make in life work. Okay, for instance, you might be interested in purchasing a certain house. Okay, so then you're in the market for a certain amount of time. You constantly keep evaluating, and at every stage you're contemplating whether should you buy or should you not, and so on and so forth. Similarly, for someone might be interested in going up for higher education, they might be thinking, should I work for a few more years or should I enroll in a graduate program or should I switch jobs? All these things are dynamic decisions that people keep making over time. And so we can think about the whole dynamic choice process in the same way as how we saw the static models. So you have a bunch of attributes or states, and there is some optimization model that. So this is what the decision maker does. There's some optimization model, and that gives you an action or a set of actions that you can take. So in the case of static models, this was just finding the maximum in a bunch of numbers. What's the maximum of the utility from a car or a bus, and then whichever gives you the higher utility, you're just going to choose that option. When it comes to a dynamic choice model, what goes in here is a Markov decision process. So there is some uncertainty about the future. So you kind of evaluate what's the likelihood of being in a certain state, and kind of evaluate what's the value of being in those states and so on. And then you choose a series of actions. For every time step, you kind of figure out what's the best thing that I should be doing. Now, when it comes to the analyst's world is a bit different. The attributes or states are not fully revealed. Just like in the static models, there are some observable components, and then there is these epsilon terms. So the analyst assumes that there is these observable attributes contribute to the utility function in a linear fashion, parameterized with these parameters beta, and these two together can address this particular question, assuming that the same model is being used. Like, let's say you are using the analyst also uses an MDP. The analyst can kind of figure out what's the probability that I see that exact series of actions. And once I have those probabilities, I'm going to tweak these parameters again and again to kind of maximize that probability, just like how we saw in the case of static models. Okay, so this is the broad framework in which the static as well as the dynamic choice models operate. It's just that this part is different. The optimization model that's running in people's heads is like earlier it was choosing a bunch of numbers, maximizing a bunch of numbers. In the case of dynamic choice models, they are evaluating not just one action, but what might happen in the future is also contributing to what they are doing at this current step. Okay. All right, so let's kind of extend some of the notation that we saw earlier. So if, let's say, time, there are finite number of time steps. Just to give you a context about how this is going to be used in the case of hurricanes, individuals are constantly evaluating whether they should evacuate or not. And they get some data about what's the intensity of the hurricane and where it is currently located, when it's going to make landfall, and so on and so forth. So these are things that change over time, and they get to decide what actions need to be taken at each of these time steps. Okay, so there are a finite number of them. And then, so we'll index these actions, we'll put a subscript T to indicate time. And they have information of the state vector xt comma epsilon t. Okay, again, this is observable only to the decision maker. X, on the other hand, is observable to the analyst as well. So again, like before, we'll parameterize the utility functions and try to uncover those parameters using data. And like I said, xt, you can think of that as representing hurricane conditions as well as socio-demographic factors. Like you might know how many individuals are in the household, how many vehicles do you have for evacuating, what's the average income, the kind of house, how long was it built, will it sustain that particular event or so on. So these are some of the things that can go into this attribute vector xt. Okay, so like before, we'll construct these probabilities, but now these probabilities are dependent on the time t. Okay, so it's a very similar expression. So the probability that the analyst would assume that the individual takes action AT given state vector AT is this the action AT being great, giving you better utility than any other action that you can have taken at that time step t. Okay, so this expression is very much like what we have before. I've just replaced the use with v and also added a time index t into it. Now these variables vt are also what's called the conditional value functions. So these tell you what's the utility from. So earlier it was just the a linear parameterized form of utility function, which was like beta naught plus beta 1 times travel time of a car or travel time of a bus. But this, on the other hand, captures what utility you would receive in the next time period, as well as what you might receive from the future. It has in it embedded an expectation from everything that's going to happen one step down the line. Okay, so it's not just the instantaneous utility. It's not just like the one step reward or one step cost, but it also includes what's going to happen after that one time period. So it's, you assume that it's a measure of the utility from choosing AT in this time period, and then you're going to behave optimally, and that will compute through some set of Bellman equations. So okay, so mathematically you can write this as so this u here represents these one-step rewards or one-step costs. This is like one-step utility, similar to what we saw earlier in static models, and this is everything that comes from the future. Now this, however, is also discounted with parameter alpha. So the discount factor is a standard way of modeling dynamic programs. The future might not be as important to you as it is. Like, I mean, if you convert everything into monetary units, it makes more sense. You can think of this as being related to interest rates, right? So $1 now versus $1 tomorrow is very different from each other. So that's captured through these alphas. This v bar tells you some value function from being in the state xt, and this is some sort of a transition probability function. It tells you what's, given that you're in state xt, what's the probability that you would end up in state xt plus 1. Okay. And if we make some assumptions on these error terms that you see here, something very similar to the IIT Gumbel, you can come up with again closed form expressions for the choice probabilities at every time step, which is great news, because then you can construct a log likelihood function and plug it into that whole maximum likelihood estimation framework that we saw earlier. So the whole point, it's if we can find this, we are done, but finding this requires these conditional value functions small vt. Okay, so in the next two slides, I'm just going to talk about how these conditional value functions are computed. So in order to do that, we'll first define, set up the Bellman equations for the problem that the individual is solving. So if you recall, if you think about this optimization problem, I said this was a Markov decision process that the decision maker is solving. So if you think about that problem, the state vector in that problem is the attributes as well as the unknown components or the latent variables. And the decision maker, every time the decision maker sees this state, there is a certain value associated with that state. Okay, and that is computed through a set of Bellman equations. So this here is you're maximizing amongst all possible actions that you can take. This is your one-step costs or rewards, and this is your utility that you would receive from the future. By the way, is everyone familiar with the Bellman equations for dynamic programs? Okay. So so this expectation here has to be computed over how x varies as well as epsilon varies. So for instance, x could be, you know, hurricane characteristics, and epsilon could be, for instance, fuel. Okay, you don't know what's the kind of if you get gasoline during these time of disasters, and the individual might have a good understanding of, you know, how the epsilons vary as well as how the x's vary. But as an analyst, maybe you don't have full data, so you might not know the epsilons. You might not know how the fuel prices or the fuel availability is, but you might be able to observe things related to the hurricane easily. Okay, so there are these two slightly different problems that the individual is trying to solve, and the observer is essentially trying to solve a stochastic optimization problem, where he's trying to maximize the probability of seeing the actions that the individual has taken. The decision maker, on the other hand, is again solving a simple MDP. Okay. So so like I said, the expectation is computed over both the both the x and the epsilon variables. So you have a double integral here. The first one just integrates out the epsilon, and then the second integral tells you how the x's vary. Now it's assumed that these two are independent of each other. Usually, it's hard to capture correlations between your x variables and your epsilon variables. Now, once this is done, we can define another set of value functions which are called the Exante value functions. So these are, you can think of these value functions are something that the analyst is interested in. It doesn't depend on the epsilons. It just depends on whatever is observable to both the decision maker and the analyst. Or it's like before the decision maker could see epsilons, what's the value of being in a state X? Okay, so this is before, if you can think about the state as being observable in two stages. You first see X, you first see epsilon, and then you see X, and then you make a decision as an individual. So before you see the epsilons, or let's say the prices of gasoline or the availability of that, this is the value of being in a certain state or value of seeing a certain kind of hurricane conditions. And if you make this sort of a transformation, you can simplify these Bellman equations. I'm not going to get into these details. It's just going to we're just going to integrate out the epsilons, and we come up with another set of Bellman equations which are purely in terms of these V bars. Okay, so this is something that we can compute or not in closed form, but using a simple set of simple backward induction type steps. Okay, so and again, because the epsilons are assumed IID Gumbel, the integral can be simplified, and you get something called like the log sum, and this is the byproduct of all the algebra that was shown in the last few equations. So if I know the conditional value functions, I can also estimate the ex ante value functions, and I can put all of this into a backward induction algorithm, and then compute these conditional and ex ante value functions as well as the choice probabilities, and then that goes into a maximum likelihood estimation. So is this setup clear? Any questions at this point?
So the error terms over different time steps.
Yeah.
Do you have to account for like the dependency?
Yeah, we assume they are independent. That's why we can write the choice probabilities in a closed form. Yeah.
And the value function, you you're specifying that to allow to see the behaviorally people how much they're looking ahead, right? But I guess it's possible that they might be completely myopic and it'll turn out that it'll estimate with the data.
That's a very good question. So, if you look at the Bellman equation, the alpha can be used as a parameter that kind of tells us how myopic or how forward-looking individuals are. Not everyone might be thinking about 6 hours from now or 1 day from now what's going to happen, how the hurricane is going to evolve. So the cool thing about this framework is we also estimate alpha. We can also get that from the data that we observe. We can also conclude how myopic the community or the population has been. And I'll show you some of the results indicate that it's not necessarily 1 or it's not necessarily 0. If it's 0, then there's nothing from the future. All that you care about is the immediate rewards or the costs. And if it is 1, it's you're essentially saying I really value the future. That's the maximum value I can assign to it, and so I'm going to consider its impact in the same form as what it is tomorrow. Okay, so we'll do that estimation together with the betas. Okay, so yeah, this is broadly how it reduces to. You come up with these backward induction type statements. So at the very last time period, there is nothing. There's no value associated with taking a certain action because that's the end, or the process ends there. So you can compute your ex ante value functions and switch time and reduce it by 1 step and plug it in here to get the value functions at the previous time step. So the conditional value functions that goes in here, and then you get the ex ante value functions at capital T minus 1. So you plug it in here and then get conditional value functions at capital T minus 2 and so on. So this can be like plugged into a backward induction algorithm, and the goal is, again, like I said, to compute these conditional value functions small v x comma a. Now, like before, we'll parameterize the utility functions using some betas, and this is usually in a linear structure. And then, like I said, we also can use your, we can also estimate the alphas alongside with these betas. And the another interesting feature is we can also parameterize the belief that individuals have. So if you look at this expression here, so this is telling us that the individual is currently at a state xt, and he or she thinks that it's going to go to a state xt plus 1 in the future. Now this will happen with a certain probability, but that's not, what's going on in the individual's mind is not very clear to the analyst. So the analyst can assume that this particular probability transition function is also parameterized with some set of parameters which are simple to represent. It's some sort of a lower dimensional object, and all of them put together, we'll call them the vector of parameters is lambda. Okay, so all the betas, the discount factor, the belief system, all of them are, we'll just, for brevity, we'll just call them as one single vector lambda. Okay, so once we have that, so we can write the choice probabilities just like before. It's just that now it's a function of all these vectors, and then you can set up your maximum likelihood function, which it's very similar to what we saw earlier. It's the sum of some logarithms, but now you're trying to maximize the sequence of actions the individual has taken. Okay, so if they haven't evacuated for 4 time periods and they have evacuated in the 5th time period, you want to maximize the odds that your algorithm will give you that as a solution. The probability that you would see that sequence of not evacuating for first 4 time periods and then evacuating in the 5th time period, that's what is being maximized in this particular expression, and this is done for every individual in your sample. Okay. So, and once we've done that, we get your estimates alpha, beta, and lambda, and then again you can do your hypothesis testing whether they were significant or not, and then you can also do your sensitivity analysis. That is, if you change some of these variables, how will your choice probabilities change, and consequently how will your demand changes. Now that again is not a very trivial problem when it comes to dynamic choice models, and I'll explain that using an example. Okay, so and maximizing the log likelihood function is kind of this standard Newton's method that's used, or the BHHH algorithm, where you can compute the gradients. It's not trivial. It involves again a bunch of dynamic programming set of equations and one more backward recursion algorithm to set up the gradients. And once you have the gradient, you can compute the approximation of your Hessian using your score functions and then optimize your objective. So the idea is you start with some initial values of estimation for alpha, beta, and lambda. Oh, by the way, this is an unconstrained optimization problem except for these alphas. The betas can be anything, the lambdas can be anything, but alpha is a discount factor, so it must be between 0 and 1. So the standard trick is to kind of replace alphas with some function which maps numbers from 0 and 1 to the real line, so that you can make this a simple unconstrained model. Although you don't get convexity and so on, so most likely you're going to end up with a local minima, and that's the best that we could do in most settings. So you start off with some initial values of estimates for the alpha, beta, and lambda, and then you solve the dynamic program to get the value functions. You solve another dynamic programming problem to get the derivatives, and that gives you, with that you get the choice probabilities as well as the derivatives of the choice probabilities, and hence you get the derivatives of your objective function, and that becomes your gradient vector that kind of can be used to construct your gradient vector and your descent direction, and then you repeat these steps to get from one initial estimate of your betas, alphas, and lambdas to another estimate, and you do this till some convergence is achieved. Okay, so this is broadly how the choice modeling framework works. Okay, so now what we did is we applied this framework to the context of individual decision making during hurricanes, and this was our data set. It was collected by the Public Policy Research Lab in LSU, and they had about 277 households that were surveyed and interviewed during Hurricane Gustav. That was way back in 2008, and this is the trajectory of the hurricane, and these were the locations of the households that were surveyed. And yeah, we got this from Chester Wilmot. I mean, a lot of people seem to have access to it. He's very friendly, and so he's not working on this data set anymore. So if you just write to him, I think he's willing to share. And so we looked at 16 6-hour time periods. So this is where we thought the individuals were making decisions, and we had a lot of data from the National Hurricane Center at these intervals. So this made sense to, that's when things were being updated. So we thought that's where people are making these decisions. And we also had some data on when the mandatory evacuation order was issued, but not a lot of data on when the voluntary orders were issued. Because these households, like you saw in the previous figure, kind of were scattered around. Different households got different voluntary evacuation orders. We didn't have that information in the data set. And this is a cumulative distribution of the demand. This is how about, I think, 193 households of the 277 evacuated. And this is the time periods at which people are making these decisions. And you see that, you'll see some, sudden jumps in these plots that could correspond to these mandatory evacuation orders or time of day. People tend to prefer evacuating in the morning versus evacuating at midnight and so on. And just a quick note about the hurricane characteristics. It was a Category 4 hurricane when it made landfall in Cuba, and then by the time it hit the coast of Louisiana, it was a Category 2 storm, a little less severe than some of the recent ones when it hit the U.S. coast particularly. And these were the variables that we considered. Pretty standard variables that you would see in most hurricane demand literature. So we're looking at the number of vehicles in each household, the household size, their income, how many individuals were 17 or less, and were they having pets, how many years were they in the particular house, and then a bunch of hurricane related characteristics that we pulled up from the National Hurricane website. So this is all time dependent features, like what was the distance from the center of between the household and the center of the hurricane. And then they also make forecasts about where it's going to make landfall. So the distance between the household location as well as the landfall location, this again changes over time. The intensity, which is on a scale from 1 to 5. 0, we also had a 0, which indicates it's just a tropical depression or a storm. It wasn't classified as a hurricane yet. And then there were some models that, some other features that came from a model called SLOSH, which is widely again used for understanding how rainfall and winds change over the geographical region. So we had some data about what's the probability that winds would exceed a certain number, or what's the probability that the storm surge would be greater than a certain value, 5 feet in this case, for a certain period of time. And then, like I said, we had some information about when mandatory evacuation order was issued. Okay, so like I said, these are the decisions that individuals were making. At every time step, they can either evacuate. If they do that, the choice process ends. Their next choice, of course, they do still a sequence of choices, that is where do they go, and that's a very difficult problem to capture because we don't have that kind of data. But then if they decide to wait, then in the next time period, they again have these two choices. But in the very last time step, we assume that they either evacuate or stay. Okay, so this stay option is slightly different from the wait, because when we assume that they are waiting, they are just postponing the decision. But in the very last time period, this is close to landfall, it's assumed that they are not going to evacuate anymore. They're going to stay at their households till the recovery happens. So the utilities are set up this way. So for the stay option, we just normalize it to 0. And this is done primarily to avoid identification issue. If you add in some coefficients times the attributes, you would not be able to estimate your parameters because the same attributes and coefficients appear in one of these other utilities. And the utility of evacuate option is like a linear, it's linear in the attributes of the parameters. Similarly, the wait option, you have some parameters C transpose times. Sorry, this should be xt. This is again linear. And the objective is to find, using the maximum likelihood estimation, what are the values of beta and what are the values of C. Yeah, and so we came up with these two models, slightly modifying some of the earlier discussion we had on the dynamic choice process. The first one is what we call the perfect information model, wherein we don't really have uncertainty over how the attributes change. Okay, so like I said, these attributes, you can think of them as socio-demographic factors, the table that I showed you earlier. So this is your X vector. Okay, so it has a bunch of things which don't change, number of vehicles, household size, these are all going to be the same over time. And then it has a bunch of attributes which change over time. Now in the perfect information model, we assume that everything in the future is completely known to the individual. This is a very restrictive assumption to make, but it's a good starting point. So because we are doing all of this analysis in hindsight, right? We are doing it after the hurricane has come and passed. So we have access to this information. So in the perfect information case, your dynamic programming is pretty simple. You don't have your integrals and times f times the dx and so on. You just get utilities from your current action, which is to wait, plus everything from the future. But if you choose to evacuate, you just get one instantaneous utility from evacuating and nothing else. There's no decision making after that. So there's no second term which corresponds to something from the future. And as before, we have the discount factor alpha. We can again define the ex-ante value functions, put this all these three set of equations in a backward induction, backward recursive algorithm, and compute these values, and then the transition probabilities, and then estimate alphas and betas. So this is the estimation results. So like I said, again, betas correspond to the utilities of the evacuate option. C corresponds to the utility of the wait option. And we started off with a full specification where we had everything in the model, and then we kind of threw away things which were not significant, and this was the final specification we got. But I won't spend any time in understanding what these signs represent, because this is not a very informative model, because it assumes a lot. It assumes that the individuals know exactly how the hurricane is going to evolve, what its intensity is going to be in the future, where it's going to make landfall, at what time, and so that's a lot of information which no one is going to have. But it's some sort of like a value of perfect information. If everyone knew it, then this is how they are going to behave. But we just started off with this model because it just help us with the estimation procedure and set up our code and so on. So the thing that we then did was what we call the partial information model, where we don't assume everything from the future, but we use estimates from the National Hurricane website. Now the website offers probabilistic data on the intensity as well as the distance from the center. So this information is given every 6 hours, and which is why we chose the 6-hour time windows. And this is how the website releases this information. So for instance, I don't know exactly what date is this. Maybe so Saturday at 6 a.m. I think, and it's currently telling me that the hurricane can be category 1 with 80%, 79% probability, or it could be a category 2 hurricane with 10% probability, and so on. And this is how it's going to change over time. So you get this f function that we saw earlier, the transition probabilities, but with a small twist that the transition probabilities are now time dependent. The earlier model that I showed you are just like the simple Markov processes where you forget everything after one time step. So f didn't have any time indices, but we'll add that into this mix. And then the NHC website can also gives you where it's going to be located. Where's the center of the storm going to be over different times in the next 12 hours, 24 hours, 36 hours, and so on. Okay, so it does this for current hurricanes as well as all this is archived, so you can get this data for any previous hurricane that has occurred. Yeah, so we'll modify the Bellman equations and use this data. And the way we do it is the evac option is still the same. There is nothing from the future, so it's just a linear combination of the parameters as well as your the state variables. But the wait option now has the f function that kind of reappears. So this tells us what's the value of being in a future state. And this is coming from the National Hurricane website. This is telling me what's the probability with which the intensity could be 1, 2, 3, 4, 5, and what's the value of being in those states 1, 2, 3, 4, 5, and so on. And when you do this, and you can also I'll not get into the math particularly in this particular slide, but you can also change your ex-ante value functions to kind of reflect this assumption that we made, and then again plug this into the whole backward induction backward recursive steps and estimate your value functions and put that into the maximum likelihood procedure as before. So this is what the results look like. So we just have these two time varying variables. One is the distance from the center, the second one is the intensity. This is what we get from the NHC website. All of the other ones are from the surveys. We get this from what the individuals have responded. So we get a bunch of parameters which are significant, and we can construct the log likelihood objective function, as well as notice, as I said before, we can also estimate the discount factor. And from the data, it suggests that the discount factor is 0.66. So they're not very myopic, they're not very forward-looking. It's somewhere in between. And this again is just this comes as a byproduct of the data. Yeah.
That discount factor also depends on how you
Number of intervals, yes, correct. So we did it by a 6-hour period just because that's the kind of data that's available, and it's also probably, I think I should say what these utilities mean at this point. It's easy to think about discount factors when you're thinking about money, but since the individuals are making decisions without any, there's no currency involved. The way we'd like to think about these utilities are at some sort of a discomfort level. So it's very hard to interpret what is 0.66. It's not an interest rate or something like that. So the expressions that you saw earlier, yeah. So this is the disutility or the discomfort you would receive from evacuating at this time step. This is the discomfort you would receive now versus everything from the future, and everything from the future has been, normalized or reduced by a factor 0.66. That's all. That's all that we can say about the discount factor. All right. So this is the final specification that we got with all of these parameters being fairly significant. So the last thing that we'd be interested in is what does it mean to have a negative sign, or what does it mean to have a positive sign. So this is the standard analysis that you would do in any choice models. If I see, for instance, you're looking at mode choice between a bus and a car, if you see that the coefficient of something is positive, then you can say, okay, if I change that value a bit, the probability is going to increase. If it's negative, if I change that attribute a bit, the probability is going to decrease. We could make these kind of inferences. So these are also called elasticities, right? So that information, however, is not so trivial because of the whole model setup and because you have a bunch of dynamic programs embedded in this. But we can still calculate these things using, again, it's a bit involved, and the code, it really takes a while to set up this particular computing these elasticities. But just for the purpose of illustration, I'm going to take a single variable, which is the household size. X here represents the household size for an individual n at time step t, and it's constant, so the t here is more or less redundant. And so the elasticities primarily try to understand what's this particular expression. It's the partial of the choice probabilities with respect to the household size. So if I increase the household size by 1, or if there was one more person in the household, would they be more likely to evacuate or less likely to evacuate? This is the kind of questions that we can address using choice models. And if you do the math and simplify some of these expressions that we have for these partial derivatives, it turns out to be something like this. So the first term here is the difference between the beta and the C values for the household H. Okay, so this is again coming directly from the table that we saw earlier. Plus there is a second term that is involved, which includes some of these other the derivatives of the Exante value functions, as well as the transition probabilities and so on. And this, if you notice, is a function of time. Okay, so these choice probabilities or the elasticities are now a function of time. How they respond to these changes in your covariates or your attributes it depends on when you are in this whole tree. Where if you're in the very beginning stages of your evacuation, you might have a different choice probability of evacuation versus if you're at the very last stages, you have a different choice probabilities. And we actually go ahead and compute these expressions for a bunch of covariates. And like I said, these two are constant, but this is time dependent. So this entire expression is time dependent. And this is how these elasticities look for the household size. So we notice that this is the final expression. It's all positive for up to a certain point, after which it becomes negative. Okay, so which is very interesting, because in the very early stages, it means that having an additional household member means there is a likelihood that they'll evacuate. Okay, there's a higher probability, there's a positive probability that they'll evacuate. But then after a certain point, it shows that having an extra household member in your family, the odds that which you will evacuate kind of starts to go down. Okay, so these time dependency or these time varying features can now be captured using these dynamic choice models. So you can kind of predict at what stages, and most of them have these optimal stopping kind feature, like at what point does these choice probabilities or these elasticities start flipping. So Of course, we'll also want to understand why this is happening. Okay, so for instance, the data that we saw earlier is revealing that as you increase the household size for later time periods, the probability is going to the probability of the probability is going to decrease because the sign is negative for the later households. That is for the last few time periods. As number of people in your household increases, these choice probabilities decrease. So it's probably because if there's a larger house, then there's more time is needed for preparing for an evacuation. So that could be one possible reason. So they might be very averse to evacuating versus during the later periods versus the earlier periods. So this is how the choice probability, the elasticity varies for 3 different households. So the blue one here is a household that doesn't evacuate at all. The gray one represents a household that evacuates in time step 6, and the orange one denotes the household that evacuates in time step 11. And what you have on the x-axis is the time intervals, or the different time steps, which was 1 through 16. And this is the probability with which the difference in the probability of evacuation. That is, it's because the household size is a discrete variable. It's not a continuous variable, so you can't. It doesn't make sense to talk about the partial of that. It's like a finite approximation of the partial. So it's the difference in the probability of evacuation. At some point, it's all positive. That's an additional household will increase the odds of the household evacuating, and at a later point, an additional household member will decrease the odds of evacuation for that household. And we saw this being true with years of residency as well. It stays positive for a while, after which it kind of flips sign and becomes different. So these kind of help us in predicting what's going to happen for a different scenario where it's a different hurricane and a different set of household characteristics. You can kind of predict what the demand is going to be, and then again it can be used in the whole evacuation procedure by embedding it into traffic assignment, as well as strategies like contraflow and so on. And we did this for some other variables. Here is the how the choice probabilities change with difference changes into the distance from the center. Okay, so if you have predictions about how the hurricane is going to evolve in the future, these kind of models can be used to understand what is going to be the change in the demand. These choice probabilities can be directly translated to how many travelers are going to be added to the network, or going to not, how many travels will not travel, and then you can predict what the network congestion looks like. Okay, so with that, I'll stop, and I'll take any questions if you have.
For the variables you selected for the model, you have the information for the number of people under 70 years old.
Yes.
Do you have information for elderly people?
No, I don't think so. They had also kids, I guess, kids and under 17. I don't think they had number of elderly people in that data set.
Yeah, and also for your like elasticity modifier part, which factor has the most significant effect?
So the significance can be just got from the z values. So all of these are significant. So you can see that household size and years of residency, both of them were found to be significant. But between these two, again, you'll have to, because you can't just use the magnitudes and say anything about this model anymore. You still have to go through the math and construct the elasticities, and then only tell that with a change in 1 unit of years of residency or household size, what's the change in the probability is going to be. So that has to be done through, again, the backward induction steps. Yep.
So this dynamic discrete choice model formulation that you have, you derived this, or?
No. Oh, sorry, I should have mentioned that. I forgot. So this actually is a very old field. It started off in 80s, somewhere around that time, and John Rust, who was an economist, he came up with the dynamic discrete choice framework, and he had access to a depot manager's diary in Minnesota or somewhere, and this was like a very detailed summary of all the bus engines in a particular depot. And this depot manager had this habit of writing down, when was an engine replaced, what was the mileage and every month, and how many miles was he expecting it to travel and so on. So Rust tried to fit a model to whatever the depot manager was thinking for that 10 years period. And so he wrote a bunch of papers. One is in Econometrica and the other is in, I think, CM Journal of Optimization, where he discussed the math, as well as the other one was the more applied one where he applied it to the model.
I've seen some of that, not in so much detail, but I remember like Heckman also did a lot of work on this topic too. Right?
Who was it?
Heckman, it was earlier in the 80s.
I see. I didn't.
But I think one of the issues he was dealing with was that dependency in the error, because a choice made at a certain time is dependent on the choices made in the previous times, right?
Just in fact, this estimation, this is like a very difficult thing to do. So once you add a little more, fancy things to your error terms, it becomes very challenging, because even though you have a closed form expression, you still have to solve these series of dynamic programs to get to your value functions and then the choice probabilities. Otherwise, you'll have to just simulate things.
I like it. It's pretty.
Yeah, and they've been used here and there in economics, but there's not a lot of data in the last on individual choices. But now things have starting to change. So some of these models where people can be observed over multiple, when we have panel data and they can be observed on multiple periods, I think this is a very nice framework where you can get more out of it than static choice models.
Did you try doing like some kind of validation?
Yeah, we have a very small data set, so it's kind of very tricky. Like 277 is putting out 10 15 samples, and then you want to estimate something. So yeah, I'm still like wondering what's the right way to validate this thing. So recently we are trying to get some more data from one of the recent hurricanes, and then see if we can see transferability is another issue with hurricane literature. What you fit for one region, is it going to be the same for a hurricane in a different state or a city? So we'll see if the other data set turns out to be a slightly bigger one, then we'll separate it out and validate it. Yeah, that's a valid point. Yeah.
I'm interested in the technological decision process of residents. Maybe at current time, their decisions is not whether to live or stay. Depending on the current forecast obtained from websites, they make a decision. In the future, the exact future time, they decided to leave. So only when the forecast change, they change their decision.
Correct.
They make another future in time.
Yeah. So here the forecasts are changing every 6 hours, and it's a very short, time window of just 3 days. But are you talking about general residential choice and these kind of problems?
Yeah.
Or is it in the context of hurricanes?
Yeah, it's about how residents make choices.
Yeah, usually the choices that people make about where to live, and those kind of things are slightly more long term. So your time intervals, that T1, 1, 2, 3, 4 would probably correspond to months or years. And there has been some literature on this in California where they've used land use data from like last 30 years, and they try to fit a similar model about they were looking at house owners, and they was trying to understand, will they build a house in their plot, or will they wait for the next year? So it was the time period of interest was slightly longer, 1 year.
And the decisions by different residents may be related.
Yeah, correct.
All living can be decided to live.
That's true. A lot of those effects can happen, and you could probably have your error terms, although I had in the notation indexed with N and T, they could be correlated across individuals and across time. But it's a very difficult problem to solve. But like you said, that's pretty valid. And maybe some of the decision variables can, the state or the attribute vectors can, solve that problem to a certain extent. If you have in the stated preference surveys, were you inspired by your neighbors, or did your neighbors leave or something? We didn't have any of that data. But if we have that data, that can be thrown into the model, and we could move things from the epsilons to your x vector. Some of that can be done.
Another question. So at current time, residents make decision depending on the utilities of current alternative and their expected utility in the future. So that involves addition of utilities from different decision making process. And we know that utilities are scaled so that the variance constant, maybe text row, say something like this. So does this make sense to add utilities from different decisions?
Yeah, so that's a very valid point, because if you look at the Russ' original paper, it was one decision maker making decisions over multiple periods. But later on, the field evolves. Usually, it's not a single. You don't get so much data from a single decision maker, but you get, this is what is representing a collective, some sort of a collective wisdom. It's like different decision makers data have been like put together, and you're estimating some of your model parameters. So that's fundamentally different from the original discrete choice work, where there was one single decision maker being exposed to multiple environments, and they made different decisions, and you're trying to understand what was going on in one person's mind. But now we are trying to understand what was going on like a community's mind, if that's the right word to call it. And that issue is there, of scaling those utilities across different decision makers. Yeah.
I'm looking at this. I'm surprised that income isn't significant. Do you have a sense for why that wasn't?
Some of that could be like it could come. It could be captured from number of years of residency, or there could be, those kind of effects could have happened. Or maybe household size, it's correlated with it, so those issues are there. But apart from that,
did you, I guess it was from a number of communities around southern Louisiana, right? So that's, I guess, did you, was the data like across a bunch of different income groups?
Yeah, we had fairly good variance in the income. It wasn't like unimodal and just everyone were in the same class, because the households were kind of spread out. It wasn't just in like a single parish.
There's probably some correlation with that, with the distance center, like wealthier neighborhoods, they like cluster together or something.
From the distance to center?
Yeah.
This is the distance from the household location to the hurricane.
Like, people with higher incomes might be clustered more together, so they'll have
Yeah. Some of these variables can have like compounded effects because of being present in the model, but once you take one of them, or maybe if we take away years of residency, maybe income starts to become significant.
The model assumes that the number of periods is
Yes.
unknown to the.
Yeah. So even that is a variable, because you don't know exactly when landfall is going to happen. But approximately, so we don't go all the way till the landfall. So I think it occurred on September 1st at like 9:30. So our time periods end at August 31st midnight. And we've assumed that everyone who has not evacuated after that has stayed. So yeah, there is that small component of uncertainty in like when the hurricane is going to come, because it depends on its speed and trajectory, if it's going to kind of go through a zigzag route, and then it's
One more question. For the distance center, is in distance or in travel time?
It's in kilometers. Kilometers from the household location to the center of the hurricane.
I remember you mentioned before in the like evacuation process. It's very slow, the traffic. So
traffic is slow. This is just the household location.
Household location to the
center of the storm.
Yeah.
Yeah, so we have the NHC releases the location of the center of the storm. We know the location of the household, so we just compute a haversine distance between.
I was thinking it's distance from
household. No, not the shelter. So we don't model the post decision of making an evacuation. We don't model that step. I mean, it's a very complicated thing to get data on. Where do they go after that, and put all of these pieces together.
I think it seems that the constant is so high, almost 12. That means in the worst time that most of the people might evacuate from the household.
Not necessarily. So the constant is present in all the betas for the evacuation, right? So it is it's kind of saying if all the other variables are 0, then that's the disutility from evacuating or the inconvenience you get from evacuating. So it doesn't really have some time dependence nature to it.
But considering the dimensions for other variables like household size and
Uh-huh.
residency, then it it might not be.
The magnitude really doesn't tell you anything, right? It's just the signs tell you something. In the case of static choice models, it tells you without any attributes is car preferred over bus. These kind of conclusions can be done. But here in this particular case, that's not true.
I mean, the variables are normalized, right? So
Yeah. Yeah, if I change, multiply these by 10 or 100, you'll get a slightly different set of constants. Sorry, estimates. All right. Yeah, thanks.
We have some time for like just meeting some students.
Sure, definitely.
You also work with system.
Yes.
Okay. I was there last year. I met Professor Victory.
Oh, is it?
Okay. Yeah.
Then
Also, Sita Battery.
Yeah.
She works there now. Right?
Okay. How come?
So I was in Berkeley for masters.
Oh yeah.
So,
I remember. I think I met you. Yeah, I think I met you.
Oh,
Yeah,
really?
Yeah.
Yeah, I was there briefly. I was in Bangalore.
I think I was just walking out of the building, and then I think
Oh, did you join like a couple of years ago?
I joined 2017 October.
Okay.
Close to 1.5
I
years.
see.
Good. Pretty busy.
Are you from Bangalore? Okay.
How about you?
I am from Assam. I'm from not even Guwahati. Yeah. Yeah. Well, it's good. Yeah. Are you here for TRB? Is there a big group from IISc coming?
No, not this time.
Okay.
I think I and another research scientist. That's just two of us. Yeah. So you're working job?
I'm working with Professor Osborne. Yeah. I joined last fall, so I was in between. I was taking a break. I was working in industry, and when I was in Bangalore, I was actually working for a startup in US who was setting up their Bangalore office in Cornwall. I was there, and then I was like, okay, I need to go back to academia. I missed it, and yeah, it's been good. It's been a lot of postwork.
This is your first year.
Yeah, first year of PhD, but they gave me a lot of like since I have my master's, they gave me a lot of
Transfer
you're in
credits.
Austin, right? Where is Professor Bhatt?
No, Stephen Boyles.
Okay. Because you work as a lot.
I'm actually, like I said in the beginning, maybe you came in a little late. I'm actually a networks person, equilibrium person.
Oh, okay.
The only reason I got into this thing is there's some dynamic programming which I like.
Right.
Yeah.
How does this work with like collaborations with the very do you do project collaborating with like Bangalore City or like?
Yeah. So that center that you visited, that's funded by the state transit agencies. So there's some projects that we have with them.
Okay.
Yeah. Open to implementation.
Right. And IISc, do you have to teach courses?
Yeah.
It's only postgrad, right?
It's correct.
I mean, like,
Yeah. Yeah. So the teaching load is less compared to other places. Yeah.
That's good.
So you've decided what you're working on, or it's exploring?
It's still exploring because I had a few ideas, but then that project, I wanted to work with the Vision Zero project. I think we have that they want to bring on effective penalties to zero by 2025 and like put some behavioral elements into it. But that's like, it's a long process and the data is not really available for that right now. So I'm currently working, this year I'm working on a New Jersey POC project and stuff like that. But yeah, trying to be more defined, but it's just, the courses take up so much of your time in the first year. It's just I just came back from India like last midnight.
Oh,
And still jet lag and all that. So that's the first time like in the last 2 months that I could take a break. It's like I forgot how it that course
first year is
always
always
because I took this break of 3 years. Like I forgot how to study. But yeah, it's good. I'll see you around in TRB as well. I'm going on Sunday. When are you?
Sunday.
Okay. Are you here like over? Are you staying on like over the week?
Yeah. maybe